Ever wonder how logistic regression actually finds the line, but most explanations either skip that part entirely or dive into the math so quick it leaves you feeling like you missed a step? Suddenly, there's a likelihood function, gradients, optimization, and it's not always clear where any of it came from and why we need it in the first place. This video is the missing bridge between the two. We'll figure out how the line is learned without yet diving into the heavy math, using a simple, concrete example of students passing or failing exams every step of the way. That way, when the math does show up later, it feels less like an obstacle and more like the natural and necessary next step. This is how I think about logistic regression. Consider a dataset of students passing or failing exams. We'd like to understand how study time and exam length affect a student's chance of passing the exam. A good line correctly distinguishes students that passed from those that failed. A bad line makes mistakes. Some students that passed are on the left, and some students that failed are on the right. What we'd like to do is to nudge the line in a way that reduces the number of mistakes. To understand exactly how, we need to dive into what this line actually means. For this particular group of students, it seems like the tipping point between passing and failing happens when study time exactly matches exam length. Students that studied more than the exam length all passed, students that studied less all failed. We can rewrite this equation as study time minus exam length equals 0, capturing the bare minimum amount of work a student needs to do in order to pass. Now, for any student, we can plug in their study time and exam length and get a score that represents how much work they put in. Positive means they did more than the bare minimum, negative means they fell short. And we can turn that work into a probability of passing using the sigmoid function. Moving the line is the same as changing how we define that bare minimum amount of work. Right now, that bare minimum requires studying exactly as long as the exam. But maybe you need to study much longer in order to pass. Maybe you need to study twice the exam length. In that case, the bare minimum would be study time minus 2 times exam length equals 0. So our line is actually 1 study time minus 1 exam length equals 0. Each of these values in front of study time and exam length describe the relative importance or weight in our definition of the bare minimum. By changing these values, we can change the orientation of the line. The first knob controls study time. Turning it to the left decreases the importance of study time in our definition of the bare minimum work. Turning it to the right increases it. The second knob controls exam length. Now we can steer the line by increasing or decreasing these knobs. But that only lets us rotate the line. Consider that sometimes there's a bare minimum amount of work that needs to happen regardless of the exam. For example, no matter the exam, all students will spend about an hour on administrative processes like logging into portals, downloading notes, etc. Or maybe all students already have some baseline understanding of the topic from coming to class. That pre-existing preparedness may reduce the bare minimum required. This is captured by a constant addition or subtraction to the bare minimum work. By changing this value, we can shift the line up or down. Putting it all together, we can use these 3 knobs to steer the line across the space, hopefully ending up in the right place. But now that we know how to steer, how do we know which direction to go? Let's say our line is in this position. One thing we can do is to try turning each of the knobs by a tiny bit in each direction to see what happens. Then the next best position of the line can be the combination of the best adjustments. Let's go through this step by step. We can try turning the first knob by decreasing it by 1. Okay, maybe that was a little too much. Let's maybe decrease it by 1/2 instead. By decreasing it, we get fewer mistakes. Now that that knob is set, let's move to the next one. We can increase it and decrease it. Neither of these options improves our number of mistakes, so maybe not changing it is the best option. Let's move on to the third knob. Notice that even though we're turning the third knob by the same amount, it makes the line move far less compared to the first 2 knobs. Increasing it by 1/2 reduces the number of mistakes again. With this process, we went from 3 mistakes to 1 mistake. But notice that if we had known just how sensitive the first knob was, we could have turned it even less, and the line would have been in the perfect spot from the start. So not all knobs affect the line the same. And at this particular location, for example, the number of mistakes made seems to be very sensitive to rotating the line compared to shifting it. If we could just measure how sensitive the line is to each knob, we could steer the line more effectively. But measuring how sensitive the line is to each knob is tricky. One major issue is that if we don't turn the knob enough, the number of mistakes won't change and we won't get any feedback. What's more, not all mistakes are equally severe. For example, each of these two lines is making one mistake, but in very different ways. The first makes a mistake on a student it assigned a probability of passing close to 1/2, and the second assigned a much higher probability of passing to a student who failed. Being confidently wrong is far worse than being uncertain and guessing wrong. And this is not something simply counting the number of mistakes tells us. I know what you're thinking. How could these probabilities of passing be so different? The mistake is basically just as far from the line in both cases. Great question. Notice that there are infinitely many of the same line since we can just multiply it by a constant. Multiply it by 2 or divide it by 2, the line stays the same. Which makes sense. Saying study time needs to match exam length is the same as saying twice your study time needs to match twice your exam length. But look at what happens to the probabilities assigned across the space as we multiply by 2. Now, points closer to the boundary get higher probabilities. Previously, 1 unit of work required studying an hour more than the exam length, but now you only need to study 30 minutes more in order to get 1 unit of work. So even though the bare minimum didn't change, distinguishing from the minimum is now easier. The effect is a steeper sigmoid curve. So turning the knobs not only changes the position of the line, it changes the probabilities assigned to students across the space. So instead of asking how many mistakes did we make, we can ask how confident are we about each student, and was that confidence justified? Probabilities change continuously as we turn the knobs. That continuous feedback is the key that unlocks finding the best line. It allows us to measure exactly how sensitive the probabilities are to each knob, allowing us to steer the line in a much more meaningful way. So where does this leave us? While we haven't touched a single equation yet, we've actually built a strong mental model of how logistic regression works. Think of it as a translation layer. When we dive into the math in the next video, we'll just be giving official names to the things we already understand. Those knobs we were turning, those are called parameters. The act of steering the line is called optimization. The feedback we got from mistakes is a loss function, and the sensitivity of how much the line moves is called a gradient. You now know how the logistic regression engine works, and next time we'll build one from scratch. See you there.